So to begin our discussion in algorithm complexity, we will begin, of course, with the basic concepts. This is part of our course in algorithms and data structures, and we are now in course 2, unit 4. Of course, this is an ever-changing course, so basically this order may sometimes change, or there might be hopefully there will be new units added, but in any case, you're looking for the algorithm that is about complexity of algorithms and basic concepts, okay? At this moment, course 2, unit 4. In order to speak about these basic concepts, we will be thinking about what it means for an algorithm to be fast, to be efficient. We will be then thinking about algorithm complexity. This is the name that's usually given to these ideas, to this whole discipline. First of all, let's get one quick thing out of the way. If we are talking about algorithm complexity and about how fast algorithms are, we have to consider the size of data. Basically, if my data is small, if I have few data, any algorithm will run just fine. You don't have to worry about that. And also, if I have lots of data, any algorithm will take a while. The difference is that while might be as much as the age of the universe with a very inefficient algorithm, or just a couple of seconds with an efficient one. And to know and to understand the difference in this course, we will be speaking about these complexity ideas. But all of this is a little bit abstract so far. So in order to speak about fast and slow algorithms, let's use an example. We will use as an example the problem of computing the average height of students in one particular class, in our class. Here you will notice that I have suddenly changed from speaking about algorithms to speaking about problems, this problem. Let's get the distinction between the two things out of the way too. A problem is something that we want to solve, like this one that I have just mentioned. An algorithm is, as we have seen before, a succession of steps used to solve a problem, the way to solve a problem, okay? Any problem can be solved in different ways. We can use different strategies, different sets of steps to solve one problem. Every set of steps, every strategy to solve a problem is one algorithm. So we will compare different algorithms to solve the same problem. If one is faster, it's probably going to be more efficient than the other. And for this particular problem, computing the average height of students in our class, if I was in a brick and mortar class, I would now demonstrate this particular algorithm that I'm going to define here in its Python code. Compute average traversal. Basically, I would go to all of my students in the class one by one and by turn and ask each of them their height. Every time I got a new height, I would add it up, and in the end, I would count how many students I had and divide the total addition of everyone's height by the number of students that I have. With that, I would get the average of the height of the students in my class. If we can picture how the strategy works, and it looks like a pretty reasonable thing to do, a pretty reasonable way to solve this problem. And we can model it in Python code using a list. Okay, so I'm going to consider that this behavior of visiting everyone in order, I'm going to model that using a list. So going a little bit more abstract, I'm going to consider that I have a list with the heights of everyone, and I'm going to traverse this list. And while I'm traversing, I'm adding up all the heights, and in the end I do the division by the number of elements, okay? As we are used to see, traversal loop, usually a for loop for us in Python. This is a pretty simple way to solve this problem. Uh, of course, we need more ways because we are speaking about algorithm complexity and we want to compare different algorithms. That's going to be a big thing for us in this part of the course. So let's consider another strategy. Which would that be? Consider that we do not actually have a brick and mortar, a class happening in a brick and mortar building, but we have a class that's distributed. Some of the students in this class are in cities, in countries, even in continents that are different than the one I am in. I was mentioning before, maybe you're watching this video, maybe you're visiting this course from sometime after this video was recorded. So maybe we are not even in the same timeline. So in this case, traversing the data as I did before is probably not going to be possible. I'm also pretty disorganized sometimes, so I'm going to suppose that I'm going to consider all of these students and I'm going to just remember from time to time to ask someone, but then I will not do that in a very efficient way. I will not do that very well. So what I will do is consider that I still have a list. Let's say at some point I close the definition of my class and I consider that somewhere the information of the height of everyone exists and has been more or less stored, but I'm going to access that list randomly. So while I have not visited all the positions, what I'm going to do is generate a random position in my list, and if I have not already visited this person before, I'm going to ask that person for their height and add it, just as I did before. And if I had already visited this person, I'm not going to ask them again, okay? But I'm going to keep iterating till I have visited everyone. As you can see, this is a very, let's say, silly way to do things, and that's why I have named the algorithm silly version. But basically here, I'm not going traversal mode, I'm going random mode. So I'm jumping around and I might visit the same person twice or 3 times, and then I might have visited everyone 5 times and still not have visited this guy, okay? So this is another algorithm that will eventually solve my problem, because in the end I'm adding everyone's height and I'm also dividing by the length. So I'm solving the problem. This is not an incorrect algorithm, but it's not a very efficient one, as you can probably intuitively see. It's going to take me longer than the other one, okay? So first of all, let's see if that's actually the case. Let's define a function to create random integer lists, and let's use that as my data. This will be very convenient because then I will be able to create data list, this random list of different sizes, okay? Because I'm considering people's height. I have created integer numbers from 150 to 205. Take some time to check how the algorithms work and so on, but at this point you should not have a problem understanding this. So let's run it once and see what happens. I have created a random list of 10 numbers and I have computed its average using the traversal and the silly version. And in this case, the traversal was, slower. Okay, this took 002 and this took 0007. Let's run it again. What's going on? You said the first one would be faster. Yes, here it's faster, okay? What is happening? I have run my algorithm 2 times, and the first time the first algorithm was slower, and the second time the first algorithm was faster. What is going on? Well, what's going on here is that algorithm complexity cannot be defined about the time that it takes to run the algorithm for one particular data size, especially if that data size is small. When I run any code, my computer is running my code, but it's also doing many other things that the operating system and other software need to be doing. And because of that, that affects a little bit the time that it takes to run any piece of code. However, all of these interferences are relatively small in size. Okay, so if I consider longer executions of algorithms, these interruptions will not be significant. If I run my code with very small data sizes, they might be significant and they might mislead me. That is why, for practical reasons, we do not define algorithm complexity as the time it takes to run one particular code with one particular piece of data, but as the tendency that an algorithm follows when the size of data grows. Okay? Any algorithm that I use is probably going to take longer to run if I have more data. That's something that is frequent. But a better algorithm will have a time that grows slower when the data size grows compared to a less efficient algorithm. Okay, let's see this in a more visual way. Here we have another example of running with just one data size, which is much larger, in which I illustrate that for bigger data sizes, the effect of random system things is not as important, but I'm not going to run it here because the video is going to be long enough already. What I'm going to do is consider my two algorithms, average traversal and average silly version, and I'm going to run them a few times with random lists of size starting at 10 as I had before and going up to 2500 and growing in intervals of 50, so 10, 60, 210 and so on and so forth. Okay, let's just run this. And this, I'm going to plot the time that it took to run for all the data sizes, and I'm going to get a visual representation of the tendency of the time of these algorithms, how the time of the algorithm grows, the running time of the algorithm grows as the size of data grows. The first plot that I see is the runtime for the traversal algorithm, and you can see that more or less, with some spikes due to those system things, the algorithm grows following a line. The second one grows following something that's not so linear, and I can also check that it grows much faster. Okay, when I'm at data size 2500, this is still taking 0.00014 seconds, and this is taking around 0.3 seconds. Okay, I can see that if I plot the two images together, and you can see the two tendencies together, that algorithm 1, that remember grew following loosely a line, grows much slower and appears flat in this comparison to algorithm 2 that grows in a different way. And that is my intuition for algorithm complexity. I will not fixate myself on one particular execution of the code for one particular data, but I will think about how the time to run the algorithm grows when the size of data grows. If two algorithms have different tendencies, like this one grows faster, the time grows faster, this is a worse algorithm than this one. I will say that this algorithm that grows slower is better. If two algorithms present a similar tendency, it doesn't mean that the graph is the same, just that they grow in a similar way, then I will say that they have a similar complexity, that they belong to the same complexity class. And I will also concern myself with whether or not one particular algorithm is optimal for one problem. I said that for a problem I can have many different algorithms, many ways of solving my problems, many strategies. But I will want to know for one particular problem if one particular algorithm is the best that I can do. It's the algorithm that has the best tendency. Okay. In this case, for example, the traversal algorithm visits every person in my class exactly once. Visit every piece of data exactly once. There is no way I can compute the average height of everyone without at least visiting every piece of data at least once. So because that's exactly what it does and I absolutely need to do that, this algorithm is intuitively an optimal algorithm. And as you can see, I'm making a formal argument here. My algorithm presents a tendency that I have seen here and here, and I'm reasoning that there is no better way to do this. There is no algorithm that I could ever think up that could compute the average of everyone without at least visiting everyone once. Okay, and because of that, I could say that my algorithm has an optimal tendency. So in terms of algorithm complexity, this algorithm is optimal.